All right, let's solve the following logarithmic equations. There were two strategies that we learned to solve logarithmic equations, and this was in 4.4. Depending upon what we saw in the problem, that determined the strategy that we're going to use. And it's important in these problems to always check our solutions, our proposed solutions. More important in the log equations than it is in the exponential. If you pull back and look at all five of these problems 41, 42, and 43 will all be solved using one strategy, and then 44 and 45 are going to be solved using the other strategy. What we look for in solving a log equation is, like for example 44, all terms in the equation have a log. 45, all terms, this is a term, this is a term, and this is a term, all have a log in all terms. Unlike 41, 2, and 3, where 2 doesn't have a log in front of it, nor does 4, nor does this 2. So 41, 42, and 43 will all be solved the same way. The objective is to get one log equation equal to a number, change to an exponential, and then solve the resulting mathematical equation. So in 41, we want to be sure there's no coefficients in front of the log terms. There's not here. We want to make sure we only have one log term. We do, and then we're going to change to an exponential. So to solve for x, let's get 5 squared equal to x plus 2. Continuing solving just changes to 25 and subtract your 2 from both sides. And before we say the answer is 23, in a log equation, we want to go ahead and plug 23 back in for the x in the original problem. And we're looking for negative values here so that we can throw out that answer. But when you replace x with 23 and you add 2, you're going to get a positive number, so this is a good solution. In problem 42, we've got a little work to do here. We have to put these back together. So I'm going to have one log with base 5, and because I see the plus sign, I'm going to multiply these two arguments together. We're ready to change this to an exponential equation and then solve the algebraic equation. Five to the fourth is 625. Over here, you're going to FOIL. I'm going to do it kind of quickly. If you want to pause and work out the foiling and then come back, we should be at the same place. So these three terms were the result of foiling here. Now you have a quadratic equation, so what we have to do is zero out one side and then refactor. To refactor, this should be a pretty easy factor, although this is pretty large number. But it should factor into an x here and an x here to multiply and give us x squared. Now we have to look for the factors of 1200, negative 1200 that add to positive 110. And you could do a factor sum chart, but to save some time, if you did do that, your factors are 10 and 120. We would have gotten actually negative 10 and positive 120, because if you think about the product of those two numbers right here, 10 and 120, you will get 1200. Set each factor equal to 0, and as a final step, we're going to check our answers. So x minus 10 is a 0, which means from this factor, one of the proposed solutions is 10, still needs checking. Subtract a 120 from both sides. That one's a little suspicious, not just because it's negative for sure, but we don't want any negative arguments. It's okay to have a negative number here as long as when you plug it back in, you don't get a negative number up here after the log expressions. So plug in 10 here and 10 here. 10's a good solution. If you plug in negative 120, this will result in a negative number. So that's extraneous is what we call that. So we only have one solution. Okay, 43. Let's combine these using the quotient to difference, but we're going to go from difference back to quotient. Change to an exponential. How do we solve this algebraic equation? It doesn't look like this quadratic equation, nor does it look like this linear equation. Let's square the 2, make it 4, but make it a fraction. And then what we did is we cross multiplied. So multiply the 4 into both these terms. 4x minus 8 equals x plus 1. It's a linear equation, so not as bad as quadratic. Let's get the x's on the left-hand side of the equation. I'm going to add an 8, add an 8. Looks like 3x equals 9. Divide by 3. And let's go back and check 3. 3 plus 1 is 4. Yep, that's good. That's positive. 3 minus 2 is 1. That's positive. So this is a good answer. All right, we're going to change gears. We have a different strategy on 44 and 45. We don't change to an exponential. We actually just remove the logs from both sides of the equations, but we can only have one, we can only do one log removal on each side of the equations. So the left-hand side of this problem is good, but over here I need to put these together. So plus means I'm going to multiply. So x times 14 gives us 14x. So in this strategy, we just remove the log. You can't remove more than one from each side, so that's why we have to apply the properties here of logs. All right, solving this, I'd probably subtract this x over here to this positive 14. That gives me 13 x's over here, and over here I'm going to divide by the 13 to isolate x. All right, and if you plug back in 14/13 here for this x and this x, this is a good solution since we get positive arguments. All right, let's solve this log equation. So we need one log on each side if we're going to remove the logs. So plus means back to multiplication. So I would put the 8 up front of the x plus 3. Let's remove the logs. To solve this equation, let's distribute the 8 in. Now we want to subtract the 7x. That's 1x. Now we want to subtract a 24. All right, and let's go back and try negative 25. Negative 25 times 7 and then minus a 1, that's going to be negative. So this, all that work for nothing. We just respond no solution. Oh, I'm so sorry. Let me move that up. No solution. Okay, now we're going to switch gears to chapter 5. So you might want to attempt to do all the ones that you can, and then any ones that you get stuck back on, you'll have this, video to kind of look back at and kind of figure out in the video where you need to be to kind of get your questions answered. 46 says, determine if this ordered pair is a solution of the system. So if x is 1 and y is negative 9, we just took turns substituting in these values to each equation to see if it's satisfied or made the equations true. So I think the answer to that's yes. You could check the key online. I don't think I'll take time to work through that one. So I think our time is better spent maybe down here doing practice problems with these different methods for solving systems of equations. So looking at 47 and 48, we're asked to solve this system by the substitution method. For that method, we kind of inspected each of the equations and we looked to see if we had any coefficients of 1. And we certainly have a coefficient of 1 here on x, and we have a coefficient of 1 here on y. Our next move was to isolate that term having a coefficient of 1. Well, I'm noticing that in my bottom equation, y is already isolated, 1y is isolated. So I'm going to actually sub in the second equation to the first equation wherever I see y. So I'm going to rewrite the first equation, but right here where I have the parentheses, that's going to represent what y is, and y is actually equivalent to 2x minus 21. So in this method, substitution, we take one equation and dump it into the other. Notice that we got rid of the y, so now we just have to do the math here and get x's value so we can back substitute and get y. Okay, so looking at this structure right here, you're going to have to distribute this -3 in. I'm going to collect here. So we've got our calculator handy. That's going to be 12. And if you get some kind of weird number, that's probably a red flag. You probably made a mistake. All right, now to finish this problem, I'm going to go back actually and use this equation right here to find y, since I know what x is. And dump in 12 for that x. That's 24 minus 21, so that's 3. So we write our answer as an ordered pair, 12, 3. All right. 48, again, I'm using the substitution method, so my eyes should be looking for any variable that has a coefficient of 1 and then isolating that equation for that variable with a coefficient of 1. So I'm going to work with the bottom equation here. And when I add 2y to both sides of the equation, I'm going to get that x equals 2y. So I'm going to sub in equation 2 to equation 1, replacing this x with 2y. And then just write down the rest of the problem. So this becomes 10y. Now I can collect these two terms. So y is 0. So that's nice because when I plug in y here for that y, when I plug in 0 for that y, okay, I'm going to get 2 times 0, so x is also 0. So my answer is the origin, or the ordered pair 0, 0. Okay, so we've got 2 examples coming up of the addition or the elimination method. So same objective, let's solve this system of equations, but let's use a different method. So the addition method says we want to either cancel the x's or the y's as we look down a kind of a column. Just make sure the equations are all lined up, meaning the x's are underneath each other, the y's, and the constants. When we look at 49, right now the way the problem stands, if I were to add down, I'd get 2x and 2y. So let's just choose what variable we want to eliminate. If you want to eliminate the x's, then I would have to multiply the top equation by -1. So I'm going to distribute the -1 into the top equation, recording it right here. And then I'm just going to re-record the bottom equation here. And I'm ready to add down, so I do that horizontal line there. All right, let's add down. So these will cancel to 0, but oh, wait, these also cancel to 0. So we record a 0. 0 equals -2. Well, we eliminated both x and y, so that tells us that we either have the infinite solution system, where those are 2 lines that graph on top of each other, Or if we get a false statement like this means we have two lines that are parallel that never intersect. So this is actually no solution. These are parallel lines that don't have any ordered pair in common. Okay, problem 50. All right, what should we eliminate? The x's or the y's? And I think it's like 6 of one, half dozen of another. So I guess I'll just eliminate the x's. So 2 and 3 both will go into 6. So I think I'm going to multiply the top equation by -3. This term will become -6. So then I'm looking for a +6 here. So that means I'd have to multiply 3 by a +2. So let me distribute these constants in and line up the result. So -6x, that's +12y equals, and that product gives us -24. And multiplying the 2 in for all of these terms. Add down, 2y equals. Be careful here, you know, don't forget your negative sign. Be sure and use your calculator. I believe this is -6. We're halfway there. We need the x's, or the x anyway. It doesn't matter which equation you choose to replace in for y -3 to get the x. If we don't make any mistakes, we'll get the same answer. So using the top equation, I'm going to dump in where the y is, -3. So negative times negative is +12. And then continue solving. X comes before y, so we write the ordered pair, -2, -3. Okay, now we're looking at a system of linear equations in 3 variables, x, y, and z. We're asked to determine if this ordered triple is a solution. So this is x, this is y, and this is z. So if we're going to determine, we're not solving, we're just seeing if that is an intersection point. You just plug in these 3 values for x, y, and z, making certain that those replacements make a true statement. So this work is on the key. If you want to attempt that and then check the key. I think our time might be better spent looking at these last 2 problems. All right, let's solve this system of linear equations in 3 variables. It's kind of cumbersome. What we did is we decided that we wanted to reduce this system to a system of 2 equations with just 2 variables. So we kind of inspected these equations, and we really looked for any equation that has coefficients of 1 or -1. So when I kind of eyeball down and look at the x terms, I do have a coefficient of 1. That's a possibility to eliminate the x's. This y has a -1 coefficient. I kind of like that because these other 2 y coefficients are positive. Same thing here. We have a negative, when you look down at the z terms, I've got a -1 here. I think I'm going to try and eliminate the y's. So what I'm going to do is I'm going to pair equation 1 with equation 2, and then I'm going to pair equation 1 with equation 3. So I'm going to pair equation 1, the first and the second equations. So let me first rewrite them as they are, the first and the second equations. So I'm eliminating y's. So when I want to eliminate y's, I would multiply the top equation by 2 so that those would cancel. I'm going to kind of do this squiggle. I'm not ready to add down. I'm going to multiply 2 inside here and re-record it here. forget, multiply 2 by everything. And then bring down the second equation. Now straight line sum bar there. Adding down, I have 13x. Those are gone. Collecting. And then adding. So that's on hold right now. Now I'm going to pair the first and the third equation. I want to eliminate the same y's. So I'm going to multiply the top equation again by 2, which I've already done over here. Now let's add down. Okay, now next move, I'm going to take these two equations, I'm going to come over here. Now I can just work with these two. A lot of places to make small mistakes that could make this problem ugly. So just always be checking your, your computations with the calculator. Okay, so what should we get rid of, the x's or the z's? I think I would multiply the bottom equation by -3 because in doing so, I'd be able to cancel with the 3z up here. Distributing, never more important than using your calculator here. Okay, I believe this is -29x. And nicely, this is +29. A third of the way there. We know what x is. So now I'm going to find z. I don't want to find y until the very end. Okay, at least in this problem. So now if I got x equals -1, choose one of these two equations to find z. So 13x, I'm going to leave a little space here. And then -13. Why doesn't that look right? Oh, that should be a negative. I could see it was going to work out to be a pretty ugly number. I just forgot the -4 there, so that's 9. Okay, as a final step, now that we have x and z, let's go back to the original problem, choosing one of the equations up there at the top to find y. I'll just work with the top equation. So 6x, which I have, minus y, which I don't have, plus 2z, which I do have. So let's see, x was -1 and z was 3. So this is -6 minus y, and then this product is 6. Let's clean these two numbers up. They happen to cancel. That's kind of a blessing. So -y equals -1. Divide both sides by negative. So it looks like y is going to be +1. So let's gather up all these variables here that we found and putting them in the correct order, x, y, z. This is going to be the solution, our ordered triple to our system of equations. Okay. 53 is similar. I think I'll just leave that for you. I think what I did on the key was I eliminated the z's because I had two z terms that have a negative with it. So that's how I approached it, but it doesn't matter. You could eliminate the y's, and if we did everything correctly, we'd end up with the same ordered triple. You could eliminate the x's if that's what you chose to do first. It doesn't matter. If we did all the work correctly, we would end up with the same ordered triple. Okay, all right, that's it.